So this example is a continuation from the previous example where we took these two minimization problems, problem A and B, and we constructed their dual maximization problems over here. So now that we have that, we're going to solve these minimization problems by turning these maximization problems into a tableau. So we'll start with letter A here. So what we'll first do is we'll take this dual problem here and we'll write it as linear equations with slack variables. So we'll have 2x plus 3y, and then put in that slack variable. We'll use u, and that equals to 21. Then we have 5x plus 7y, and we have to introduce a slack variable, and of course it's got to be different than this one up here, so we'll use v, and that's equal to 50. Then of course we have to include the objective function here, in which we have to include or write the variables all on one side of the equal sign and 0 on the other. So this will be negative 12x minus 17y plus p, and that'll be equal to 0. So now that we have this, we'll go ahead and make the tableau. So we'll go and we'll put it over here. We have x, y, u slack variable, v slack variable, and the objective function. Then we'll put in a bracket. And we'll put in 2, 3, 1 for the slack variable, 0 and 0, put in our vertical line. And this will be 21. Then 5, 7, 0, and then 1 for the v slack variable, then 50. And then, of course, negative 12, negative 17, 0, 0, 1, 0, and then we'll close off our matrix here, and we'll put in our horizontal line. So here is the simplex tableau created from the dual problem here for this minimization problem here, and we're going to use this. We're going to solve this obviously with row operations, and the solution that we come up with for here will be the same solution for the minimization problem here. So we'll do that. So of course the first thing we have to do is determine our pivot column, and that is the most negative value in the last row here, and of course that's 17. So this will be our pivot column. So then our pivot row, we then take the values in there and divide it into the constants here. So 21 divided by 3, that's 7. And then 50 divided by 7, well, that's around 7.1. So 3 will be our pivot value. So then we could start off with 1/3 of row 1. Put in our bracket. 2 times 1/3, that's 2/3. 3 times 1/3, that's 1. 1 times 1/3, 1/3. Then we have 0, 0. Put in our vertical line. 21 times 1/3, that is 7. Close off our matrix. And then we just bring over the rest. Put in our horizontal line. There we go. So now we could target this element here. So that's row 2 minus 7 of row 1. So we'll continue down over here. 2/3 times 7, that's 14/3. 5 minus 14/3 is 1/3. 1 times 7 is 7. 7 minus 7, add 0. Of course, that's the whole idea. 1/3 times 7, that's 7/3. 0 minus 7/3, that's negative 7/3. 0, 0, bring down the 1. 0, 0, and 0. Put it in our vertical line. 7 times 7 is 49, and 50 minus 49 is 1. Close off the matrix and copy over the rest. Put in our horizontal line. So now we target this element here. So we could take row 3 plus 17 of row 1. Put in our bracket. 2/3 times 17, that's 34/3. And negative 12 plus 34/3 is negative 2/3. 1 times 17 is 17. Negative 17 plus 17, that's 0. 1/3 times 17, that's 17/3. 0 plus 17/3, that's 17/3. 0, 0, and 0. 0, 0, we bring down the 1. Bring down our vertical bar. 7 times 17 is 119. And 0 plus 119 is 119. Close off our matrix, and we fill in the rest. And finally, of course, put in our horizontal bar. So now we turn this into a unit column. And of course, then step 3 says then we look to see for a solution to see if there's any non-negative values here. And there aren't. We have a negative value right here. So again, this was our first iteration, right? But we'll continue again, coming up with a pivot value for this column here. So this will be our pivot column. So then we'll take 7 divided by 2/3, and 7 divided by 2/3 is 10.5. And then 1 divided by 1/3 is 3. This 1/3 here will be our pivot element. So then we could take 3 times row 2 3 times 1/3, there's 1. 0 times 3, that's 0. Negative 7/3 times 3, that's negative 7. 1 times 3, that is 3. 0 times 3, that's 0. Bring down our vertical bar. And 1 times 3 is 3. Close off our bracket. And we go ahead and fill in the rest. Put in our horizontal line. So now we can target this value up here. So we'll take row 1 minus 2/3 of row 2. We'll put in a bracket down here. 1 times 2/3 is 2/3. 2/3 minus 2/3 is 0. 0, 0, carry the 1. Negative 7 times 2/3, that's negative 14/3. And 1/3 minus negative 14/3, or in other words, 1/3 plus 14/3 is 5. 3 times 2/3 is 2, and 0 minus 2, that's negative 2. 0, 0, and 0. Bring down our vertical line. 3 times 2/3 is 2, and 7 minus 2 is 5. Close off our bracket and fill in the rest. put in our horizontal line. So now we can target this last value right here. So we'll take row 3 plus 2/3 of row 2. One times 2/3 is 2/3. Negative 2/3 plus 2/3, 0. Of course, again, that's the whole idea. 0, 0, and 0. Negative 7 times 2/3 is negative 14/3. And 17/3 minus 14/3 is 1. 3 times 2/3 is 2. And 0 plus 2 is 2. 0, 0, bring down our 1. Put it in the vertical bar. 3 times 2/3 is 2, and 119 plus 2 is 121. Close off the bracket, and of course we carry over the rest. So now we change this into a unit column, and of course step 3 says look for negative values. We don't, so we have completed the solution for this minimization problem. We're done. Now the solution here is for our dual problem. So if we did P, that's equal to 12x, and x here would be 3, plus 17y, and of course y right here would be 5. That's equal to 121, which is the solution here. Now, the fundamental principle of duality states that the optimal solution of the minimization problem is going to be the same as the optimal solution for its dual. So the solution for here, for C here, is also going to be equal to 121. However, the values for x and y in the dual problem here, x is 3 and y is 5, is not the same as for here. The values of the optimal solution to the primal problem, and in this case the minimization problem, appear within the columns of the slack variables in the last row. So we could see if this is x, y, u, v, and p. Here is our slack variable u. We could see right here it's 1. And our slack variable for v, we could see right here, is 2. Those are the solutions for the minimization problem here. Those will be the values for the x and y here. So if we just go from left to right, this would be x and this would be y for our minimization problem here. Then we would have C is equal to 21x, and we're going to treat this as x. That's 1. Plus 50 y, we treat this as y, that's 2. There's our 121. 21 times 1 is 21, and 50 times 2 is 100, and 21 times 100 is 121. So the solution to the minimization problem is C is equal to 121, and that's where x is equal to 1 and y is equal to 2. So we'll do the same process for letter B. So let's try letter B. So the same again, we're going to take the dual problem here and write it as linear equations with slack variables. So we'll have x plus 7y, and our slack variable, again, we'll use u. That's equal to 14. 2x plus 6y. Put in our slack variables, got to be different than this one. We'll use v. That's equal to 20. And then, of course, we'll put in the objective function here, moving the variables over to the other side. That'll give us negative 4x minus 20y plus p, and that's going to be equal to 0. So then from here, we'll build our simplex tableau and use that to solve the minimization problem. So again, we'll go x, y, u, v, p. We'll put in a bracket here. Put in 1, 7, 1 for our slack variable, no v slack variable. Put in our vertical bar, and 14. Then 2, 6, 0, 1, 0, and 20. Then negative 4, negative 20, 0, 0, 1, 0. Close off the bracket and put in our horizontal line. So again, we'll start with finding a pivot element, and then from there using row operations to solve. Here is our most negative value in the last row, so this will be our pivot column. So then we'll take each element here. We have 14 divided by 7, that's 2. And 20 divided by 6, that's around 3.3. So then 7 is going to be our pivot element. So then we'll take 1/7 of row 1. Put in our bracket. 1 times 1/7, that's 1/7. 7 times 1/7, that's 1. 1 times 1/7, 1/7. 0, 0. Put it in our vertical bar. 14 times 1/7, that's 2. Close off the matrix and copy over the rest. Put in our horizontal line. Now we can target this element here. So we'll take row 2 minus 6 of row 1. We'll continue over here. 1/7 times 6, that's 6/7. And 2 minus 6/7, that's 8/7. 1 times 6 is 6, and 6 minus 6, of course, is 0. 1/7 times 6 is 6/7, and 0 minus 6/7, that's negative 6/7. 0, 0, bring over the 1. 0, 0, and 0. Bring down our vertical bar. 2 times 6 is 12, and 20 minus 12 is 8. Close off the bracket and fill in the rest. Put in our horizontal line. And now we can target this element here. So we'll take row 3 plus 20 of row 1. One-seventh times 20, that's 20/7. Negative 4 plus 20/7, that's negative 8/7. 1 times 20 is 20, negative 20 plus 20, again that's 0. 1/7 times 20, that's 20/7, and 0 plus 20/7, that's 20/7. 0, 0, and 0. 0, 0, and bring down the 1. Put it in our vertical bar. 2 times 20 is 40, and 0 plus 40 is 40. Close off our bracket, and of course bring over the rest. Put in our horizontal line. So now we change this into a unit column. Again, step 3 then says look for negative values, or the most negative value, and of course we have one right here. So this will be our next pivot column here. So then we continue. And of course this is our first iteration. But we'll continue. So from our pivot column, 2 divided by 1/7 is 14, and 8 divided by 8/7 is 7. So this is going to be our pivot element right here. So then we'll take 7/8 of row 2, put in a bracket, 8/7 times 7/8, there's 1. 0 and 7/8, there's 0. Negative 6/7 times 7/8 is negative 3/4. 1 times 7/8, that's 7/8. 0 and 0. Bring down our vertical bar. 8 times 7/8 is 7. Close off our bracket and fill in the rest. So for this value up here, then we could take row 1 minus 1/7 of row 2. So we'll go down here. 1 times 1/7 is 1/7. 1/7 minus 1/7, there's our 0. 0, 0, and we'll bring over the 1. Negative 3/4 times 1/7 is negative 3/28. And 1/7 minus negative 3/28, or in other words, 1/7 plus 3/28 is 1/4. 7/8 times 1/7 is 1/8, and 0 minus 1/8, that's negative 1/8. And 0, 0, and 0. Bring down the vertical line. 7 times 1/7 is 1, and 2 minus 1 is 1. Close off the bracket and bring over the rest. Put in a horizontal line. And finally, we can concentrate on this last value here. So we'll take row 3 plus 8/7 of row 2. One times 8/7 is 8/7. Negative 8/7 plus 8/7. Again, that's the whole idea. We have 0, 0, 0, and 0. Negative 3/4 times 8/7 is negative 6/7. And 27 minus 6/7 is 2. 7/8 times 8/7 is 1, and 0 plus 1 is 1. 0, 0, bring down the 1. Bring down our vertical line. 7 times 8/7 is 8, and 40 plus 8 is 48. Close off our bracket and bring over the rest. Put in our horizontal line. So now we change this into a unit column. So then step 3 says look for negative values here. And there aren't any. So we're done. Now again, the fundamental principle of duality states that the optimal solution, and for here it's 48, but this is 48 for the dual problem, but the solution for the minimization will be the same as that for its dual. So we have P that's equal to, we have 1 right here, that's 7. So if we take 4 times 7, plus, and we've got 1 right here, and that's 1, plus 20 times 1, that's equal to 48. The solution for 48 is going to be the same for the minimization problem, except the values for x and y are going to be different. And of course, the values for the optimal solution to the primal problem are going to be found right here, 2, and right here, 1. So if we make this x, just reading from left to right, this is our slack variable column, this one here for u, and this one here for v. So we just make this as x and y. So then if we have c up here, that's equal to 14x, but x is recognized as 2 right here, plus 20 y right here, and we recognize this as y, so that'll be 1. And then, of course, is equal to 48. 14 times 2 is 28, and 20 times 1 is 20, and 28 and 20 is 48. So the solution is c is equal to 48, and that's when x is equal to 2, and y is equal to 1. So here we've shown that in order to solve for a minimization primal problem here, we wind up solving for its dual maximization problem. The solution that we come up with for the maximization problem is going to be the same solution for the minimization problem. And then the values of the variables are going to be found, or they're going to appear in the last row of the columns of the slack variables. But there you go.